Dear students, in last lectures we already discussed the SN2 reaction, the general example of SN2 reaction, mechanism, energy profile diagram, and the stereochemistry of SN2 reaction. So today we are going to discuss the SN1 reaction. The SN1 reaction is nothing but the substitution nucleophilic unimolecular reaction. And when we take a simple example, when you take a tertiary butyl bromide, and when tertiary butyl bromide is hydrolyzed in aqueous NaOH, and then there is formation of tertiary butanol, and we get this is a leaving group. So this is a general example of the SN1 reaction. This is a tertiary butyl bromides is hydrolyzed in presence of NaOH or aqueous NaOH, and there is formation of a product that is a tertiary butanol, and there is a Br minus is a leaving group. Once we see this general example, then we see the kinetics. What is the kinetics of this reaction? Means we remember why we stand for SN1. One stand for the unimolecular reaction. Means the rate of reaction is totally depends on only one molecule, or that is a tertiary butyl bromide. So what happened in this case? The kinetic study of this reaction shows that the rate of reaction is directly proportional to the concentration of tertiary butyl bromide. And when we rewrite the equation, we call rate is equal to K1, that is a concentration of tertiary butyl bromide. Means K1 is it is a rate constant first order. Means the rate of reaction is totally depends on the concentration of tertiary butyl bromide, and the rate of reaction is not depends on the nucleophile OH minus. So that's why this is the first order kinetics, and K1 is called as a first order kinetics. So we remember the SN1 rate is totally depends on the substrate, that is a tertiary butyl bromide, and the rate is not depends on the concentration or the nature of nucleophile, that is the OH. Once we see this, because what happened in case of the SN1 reaction, the rate of reaction is not depends on the nucleophile. Means what? Means in rate determining step or RDS, only tertiary butyl bromide is taking part in a reaction, or it involved in a reaction. And what happened? The attack of nucleophile takes place in a fast step. Means we remember in SN1 what happened? There is formation of a carbocation. Carbocation is a planar, and up to the formation of a carbocation, what happened? There is a rate determining step. Means in rate determining step only the tertiary butyl bromide is taking part, and once the carbocation is formed, then the next step or second step is the attack of nucleophile, and this step is a fast step. So the rate of reaction is not depends on the nucleophile, the nature of nucleophile, or the what is the nature of nucleophile is there. Then we see what is the proposed mechanism of this reaction. The mechanism. And when we write the substrate tertiary butyl bromide, this is the first step, and this first step is a rate determining step or slow step. Formation of carbocation, and once the carbocation is formed, then this carbocation is a planar in nature. We remember this carbon having the sp2 habitides. When we see the carbon in the substrate, it is a sp3 habitides. So what happened? You take your tertiary butyl bromide is a substrate. This is the first step. First step is a rate determining step, or it is slow step, and then there is a formation of a planar carbocation. So we remember the rate determining step. in rate determining step, only the tertiary butyl bromide is taking part in reaction. So ultimately, the rate of reaction in SN1 is totally depends on the concentration of tertiary butyl bromide or the nature of substrate, we say the commonly. And once the planar carbocation is formed, then the second step is a fast step. And in fast step, the attack of nucleophile takes place. When the attack is an attack of nucleophile OH minus is takes place from the back side. And here the attack of OH is takes place from the front side. Because we remember this carbocation is a planar in nature, and when the carbocation is a planar in nature, then probability of backside attack as well as the front side attack is equal theoretically. When we say the think theoretically, then what happens? The attack of nucleophile from the backside and attack of nucleophile from the front side is equal. When the attack of nucleophile takes place from the backside, then there is a formation of such type of product. And when the attack of nucleophile takes place from the front side like this, then there is a formation of this type of product. And we remember there. So what happened? When the carbocation is a planar in nature, it having the sp2 hybridides, this carbon having the sp2 hybridides, then due to the planar nature of the carbocation or the geometry of carbocation, the attack of nucleophile is takes place from backside as well as the front side. When the attack of nucleophile is takes place from the backside, then we get this is the, we say, the inverted product. Inverted product. And when the attack of nucleophile takes place from the front side, then we get retention product. When your starting compound or substrate is optical active, then we get inverted product as well as we get a retention product. And when we get an inverted product and retention products, then we get a racemic mixture. We get a racemic mixture. So this is a simple mechanism of SN1 reaction. There is a substrate. That first step is a rate determining step. There is a formation of a carbocation. It is a planar in nature. Carbocation having the sp2 hybridides, your substrate having the sp3 hybridides. Then the geometry of carbocation is planar in nature, and then the attack of nucleophile takes place from the back side. Then we get an inverted product. When the attack of nucleophile takes place from the front side, then we get a retention product. And when we start from your optical active compound, then we get a racemic mixture. So this is a simple mechanism of SN1 reaction. When we discuss the mechanism, then we go for the energy profile diagram. And what is the energy profile diagram? So the next point, energy profile diagram. When we plot a graph between potential energy changes with reaction coordinate, then we get here the energy profile diagram. So what happened in energy profile diagram? It having the two transition state. And what happened here? We start from your starting compound, tertiary butyl bromide. What happened here? The ionization of substrate. Then we get here the transition state 1, we get here transition state 2nd, and here we get the what is your product, that is the carbocation. And what happen once the carbocation formation takes place, then what happen in first step, attack of nucleophile takes place. And when the attack of nucleophile takes place, then there is a formation of a product. And we remember here, this is the first transition state, we call delta E1. This is second transition state, we call delta E2. So this is a simple energy profile diagram for the SN1 reaction. We start from your starting compound, then what happens, the bond between carbon and bromine is leave out, or the ionization of substrate takes place. We form the transition state. There is a formation of a carbocation, that is the intermediate. Once the carbocation is formed, then in first step attack of nucleophilicity takes place, and attack of nucleophilicity takes place, then we get the final product, that is a tertiary butanol. So delta E1, this energy is required for transition state first. Delta E2, this energy is required for the transition state second. So this is a simple energy profile diagram for the SN1 reaction. Then what is the stereochemistry? The next one is the stereochemistry. Stereochemistry of SN1. So what happened in case of SN1, we already discussed. We have seen that in SN1 reaction there is a formation of a planar carbocation. And when the planar carbocation formation takes place in a first step, and this first step is a slow step, and in second step what happens, the attack of nucleophilicity takes place. Once this is your planar carbocation is formed, then attack of nucleophilicity takes place from both the sides in equal proportion, means attack from the front side as well as the attack from the back side. And when theoretically the attack of nucleophilicity takes place from both the sides, then there is a formation of inverted product and the retention product. And when we get the inverted product and retention product, then in SN1 reaction, or SN1 reaction is end up with inversion, end up with racemization. But what happens in case of the SN1 reaction, the 100% racemizations we don't observe. So why 100% racemization is not observed in SN1 reaction? So that's why we take one simple example, that is 1-phenyl ethyl chloride. We take one simple example, 1-phenyl ethyl chloride. This is the simple example, 1R 1-phenyl ethyl chloride. And we start from this, then what happens, the first step is a slow step. There is a formation of a carbocation. When the carbocation is formed, then the attack of nucleophilicity takes place from back side. Backside attack of OH. And when the backside attack of OH takes place, then we get the product. We get this type of product. This one. When the attack of nucleophilicity takes place from the front side, front side attack of OH minus, then we get a product. We get this, and we get the mixture of these two products. And when we get the mixture of these two products, then we remember, in this case, this product we got 75%, this product we get 25%. And when we write, this is a inverted product, this is a retention product, and then we called racemization. we call the racemization. So this is a simple example. We start from the R1-phenyl ethyl chloride. This is the chiral compound or optically active compound. In first step, it is slow step, formation of a planar carbocation. Due to the planarity of this carbocation, backside attack of nucleophiles takes place, we get inverted product. Front side attack of nucleophiles takes place, we get a retention product. But in this case, we get a 75% inverted product and 25% only the retention product, and then this product, the mixture, we call as a racemic mixture. And we already discussed in SN1, the 100% racemization is not observed. Means that this 50% product formation is never possible, or mainly it is rarely observed, that is 100% racemization. But mainly or maximum SN1 reaction is end up with higher percentage of inverted product than the retention product. And why? The SN1 reaction is end up with higher degree of inverted product than the retention product. So that's why there are the two factors is responsible for that. Means in SN1, 100% racemization is not there. The more percent of inverted product is there. And why? In SN1, we get more percentage of inverted product is there. So for that, there are the two factors, they are affect on the higher percentage of inversion in SN1. And these two factors, the first factor, the stability of carbocation. The stability of carbocation. And second one, the nucleophilicity of solvent. These two factors decide, or these two factors is responsible why in SN1 reaction there is a more percentage of inverted product formation takes place. So the first case, the stability of carbocation. So what is the effect of stability of carbocations? We already discussed in SN1 there is formation of a carbocation. And when the carbocation is more stable, and when the carbocation is less stable, so what happens? When the carbocation having the more and more stability, then attack from back side and front side is more and more there, or the attack of nucleophile from the front side and back side is equal, and that's why the more percentage of racemization, means the stability of carbocation is more, then the backside and front side attack or possibility of backside and front side attack of nucleophile is equal, and that's why the more percentage of racemization is there. But when we think about this, when the carbocation stability is less, then the less percentage of racemization. So we remember what happened, the carbocation having the less stability, then ultimately what happened, the backside attack is more, and when the backside attack is more, then ultimately the inverted product is more, and when the inverted product is more, then the percentage of racemization is less. So this is the first factor is very important, the stability of carbocation. We already discussed carbocation is more stable, then the attack of nucleophile from the back side as well as front side attack is equal, and then the more percentage of racemization. When the carbocation having the less stability, then attack of nucleophile from the back side is more and more, and then the percentage of, or there is a less percentage of racemization. Then what is the second point, that is the nucleophilicity of a solvent. Means we remember, suppose here we take an example of water. Water is a solvent and water is also act as a nucleophile. And in such cases, what happens, the nucleophilicity of solvent means solvent itself, it act as a nucleophile. Then what happen in SN1 reaction? So what happen, the every SN1 reaction, what happen? There is a bond between carbon and bromine is leave out, and this bond between carbon and leaving group is leave out, and there is formation of a carbocation. So energy required to break the bond between carbon and bromine is provided by the solvent by solvation process, and this solvation process takes place like this. Means we take the example of general example RBR, that is a delta negative charge, this is delta positive charge. Here suppose we take water as a solvent, and water we already know the water is act as a nucleophile itself. And what happen in first case, we say this is the A case. Then in second case, what happen, the water molecule is surround between this substrate, or water molecule is surround this the substrate is there. I mean, this is RBR is a substrate, and around that substrate there is a water is there, or your solvent is there. This is called intimate ion pair. We call intimate ion pair, or we call this is a positive charge, we write here the negative charge. Means we remember, you take your substrate, we use your water as a solvent, water is act as a nucleophile. Then in first case what happened, in B case there is formation of intimate ion pair, means this R plus and this Br minus surrounded by the water molecule. Then then what happened, this R plus and Br minus is separated by water molecules. Means this carbocation and leaving group, they are separated, and in between, not separated, but in between these two there is a water molecule is insert, and this is called solvent separated ion pair. And this situation we call C. And lastly what happened, this R plus means the carbocation and this leaving group, they are separated from each other. They are separated from each other, and this is called completely separated. Ions. Completely separated ions, or we call completely separated solvated ions, and this situation is called the D. So what happened, we discuss in SN1 the bond between these carbon and Br is break, it require energy, and this energy is provided by the solvent molecule through the solvation process. And what happened, how the solvation process takes place. Suppose we use water, and then in this way the solvation process takes place. You take A situation, this is your substrate, then there is formation of intimate ion pair. B, in intimate ion pair what happened, the solvent is surrounded by the R plus and Br minus. Then what happened, these two, in between these two charge, or this is a R plus and Br minus, the water molecule is insert, or your solvent is there, and this is called the solvent separated ion pair. That is the third situation, or C situation is there. And in last case, both the ions, that carbocation and leaving group, they are separated by the solvent molecule. When then such type of solvation process takes place, then what happen? When we see the example of A, in this case there is no attack of nucleophile from the front side as well as the back side. But when we take a intimate ion pair formation is there, then what happened, your water molecule is there here, and suppose your water molecule is act as a nucleophile, then in B situation your water molecule or your nucleophile is attacked from the back side. So what happened in the B situation or B case, the nucleophile is attacked from the back side only, because your solvent itself act as a nucleophile. So that's why this solvent molecule or this nucleophile is attacked from the back side in a situation B, but the front side attack is a block. Why the front side attack is blocked? Because there is a Br minus, and that's why the front side attack is never possible in a B situation. So what happened? In a B situation, only backside attack is possible. When we think about the next situation or next point, this is the C situation, or solvent separated ion pair is there. Even the C situation, what happened? These two ions, they are not separated from each other. They are not separated from each other. But even what happened here, the backside attack of nucleophiles takes place here, and the front side attack of nucleophiles never takes place here. We remember. So that's why what happened in the B situation, the backside attack is there. In the C situation, there is a backside attack is there. But when we see the last case D, the completely separated ions, here your carbocation and leaving group, they are separated from each other. And then in this D situation, the attack of nucleophiles takes place from the back side as well as the front side attack takes place. So when we see the solvation process and we see all these steps, we see the B steps, backside attack is possible, front side attack is not possible. In C case, the more and more backside attack is possible. Again, in this case, what happened? In D situation, the attack of nucleophile from the back side as well as the front side attack is possible. So that's why when we see nucleophilicity of solvent is there, when your nucleophile itself act as a solvent is there, then SN1 reaction is end up with less percentage of racemization, or the SN1 reaction is end up with more percentage of inverted product. In which case, when your solvent is act as the nucleophile itself. So in this way, we remember that this part. Then what happened? The next important point is the stability of carbocation. The next part, the stability of carbocation. The stability of carbocation. So which factors they are decide the stability of carbocation? So according to the law of electrostatic, the stability of carbocation is increases when the positive charge is dispersed on other groups. Means when the positive charge is dispersed, then the carbocation is more stable. When the positive charge of carbocation is intensified, then the stability of carbocation is decreases. And when we take this is a G is a group which are attached to the carbocation, and when G having electron donor, and in second situation we take this G having or electron withdrawing group. Or electron withdrawing group. So what happened here? We remember what is your law of electrostatics? The G, or this is a carbon having the positive charge. This positive charge is dispersed, then carbocation is more stable. When the positive charge on this carbon is intensified, then stability of carbocation is decreases. So what happened? The G group, which is attached to the carbon or this carbocation, it donates the electron, and when it donates the electron, the positive charge or positive character of carbon is decreases, and ultimately this carbocation is more stable. Means electron donating groups are attached to the carbocation, then the stability is more. When electron withdrawing groups are attached to the carbocation, then it withdraws the electron from this carbocation or this carbon, and this positive character of that carbon is increases or it intensify, and ultimately when the electron withdrawing groups are attached to the carbocation, then the stability of carbocation is decreases. So in this way, we remember when electron donating groups are attached to the carbocation, then its stability is decreases. Either it is electron donating inductive effect is there, or electron donating resonance effect is there, then the stability of carbocation is more and more. And when electron withdrawing groups, means electron withdrawing inductive or electron or groups which gives the minus I, electron withdrawing inductive effect, or groups which are attached to the carbocation, which gives the minus R electron withdrawing resonance effect, then these positive charges intensify and the carbocation stability is decreases.